Right, we're going to cover Dirac's using All's theorem, which is way quicker now. So remember, Dirac says let G be a simple graph, and if G has order greater than or equal to 3, and the minimum degree of all the vertices is greater than or equal to n over 2, then G has a Hamiltonian cycle. So now the nice thing about this is, if you look at All's, you have the situation where all the ones which are non-adjacent fit the condition that the degree of U plus the degree of V is greater than or equal to n. But here you have the minimum degree is greater than or equal to n over 2, which means all your vertices have a degree greater than or equal to n over 2, which means any of the non-adjacent vertice pairs is going to fit this. And that means that we know the closure of G is going to be Hamiltonian, because we've already proven that the closure, if it fits All's theorem, which this one does, then that graph is Hamiltonian, and that graph is Hamiltonian because the closure is Hamiltonian. So let's just go through the process. We have All's theorem. If it fits those conditions, then the graph is Hamiltonian. Why is the graph Hamiltonian? It's Hamiltonian because the closure is Hamiltonian. And remember, we have that if and only if the closure is Hamiltonian is the graph Hamiltonian situation occurring. So let's just write this a little bit neater. So for our proof, we're going to prove this directly, where we say, okay, we have all our vertices, so we let for all vertices, which is the element of the vertices set, the degree of the vertex be greater than or equal to n over 2, with the order of G equal to n. So that's actually, we're proving directly, so we say, okay, let all the vertices, which is element of the vertices set, have a degree V greater than or equal to n over 2, which is just the conditions of A, basically. And then we say, if G is the complete graph, it is Hamiltonian. And if it is not the complete graph, then if not, Kn, we look at UV, which is not an element of the edge set. Then du plus dv is going to be greater than or equal to n upon 2 plus n upon 2, which is equal to n. And so for all those non-adjacent vertice pairs, we have it satisfying All's condition or All's theorem. Therefore, by All's theorem, we have that situation where it fits All's theorem, and therefore it is Hamiltonian. And we are done.